Today we're going to talk about section 4.8, which is applications of logarithmic functions. We're only going to hit a few, but logarithmic functions are very useful in lots of sciences and engineering and research and all kinds of different things. The ones we're going to look at are in chemistry, we're going to look at pH. In physics, we're going to look at the Richter scale for earthquakes. And for education, we're going to look at information retention. We're also going to review the exponential growth model that we use for compound interest and add a little extra with that. So let's start with chemistry. So for pH, you may know that the pH of a substance is equal to negative the log of, this is the concentration of hydrogen ions. And it's in moles per liter. If you haven't taken any chemistry, this may seem a little bit odd, but moles is a unit that tells how many atoms or molecules or something are in the substance, so moles per liter. So for example, if we have a pH of 8.4 and we want to know what our concentration of hydrogen ions is, well, how would we solve that? Well, we just plug it into this formula here. So our pH is 8.4, and that equals negative the log of the concentration of hydrogen ions. So we do some algebra. First we divide by that -1, and then we remember what a log means. Remember, this is a common log because there's no base, so that means its base is 10, and it's the base to this power, and that equals the concentration of the hydrogen ions. So we put that in our calculator and we get 3.9811 times 10 to the -9th moles per liter is our answer. Let's try a different one. What if we know the hydrogen ion concentration. It's 3.2 times 10 to the -6 moles per liter, and we want to know what's the pH. So again, we use this formula here. We plug it in, we have the pH equals negative the log of 3.2 times 10 to the -6. Now remember, this is scientific notation, and if you haven't noticed already, there's a button of the little capital E. It looks like this, and it's one that you're going to have to hit the second, I believe it is, on your calculator. It's above the comma, and if you type in 3.2 E -6, that's your scientific notation. You can also do 3.2 times 10 to the -6. You'll get the exact same thing. Anyway, if you calculate that out, you end up with a pH of 5.5. So this formula here uses logs for something practical, chemistry, pH. Now what about in physics? One thing in physics that uses a log is the Richter scale. So the Richter scale tells the magnitude of earthquakes. So our magnitude for the earthquake is equal to the log of I over I naught. This is the intensity of the earthquake, and this is a constant. It's called the standard magnitude of minimum intensity. All right, so how will we use this? Well, let's say we have this question. If the intensity, that's I, is 2,511,886 times that of I naught, what is the Richter scale value? So what's M? So we're looking for M. We know what I is in relation to I naught. So what we have is M equals the log of 2,511,886 I naught, because that's our intensity. It's this times your I naught over the I naught, which of course means those cancel out. So we're just taking the log of this big number here, and we get 6.4. So our earthquake, we would say, was a 6.4 on the Richter scale. So what if we say, instead of this, it's 79,432,823 times I naught. Same thing, plug it in. M is the log of this huge number times I naught over I naught, so those cancel. We take our log of this big number and we get 7.9. So here's our Richter scale equation. Most of the time you're going to be given the intensity in terms of the standard magnitude of minimum intensity, so that you don't actually have to know what that constant is, so that you can plug it in and get a log. Remember, this is a common log, so it's base 10, and it's on your calculator. You just hit the log button. Now, in education, we have something called forgetting curves. Someone did research and actually put an equation to how quickly you forget information. So we have this equation, S of t. Remember, this is not multiplied. It's just saying that S is a function of t, equals A minus B times the log of t plus 1. So A and B are constants. They're found by experiment, and they differ depending on the class and the material you're covering. Like, for example, for our math class, we'd have specific A and B for our equation. And then this T is time and months. So if we're given a formula for the average score of an exam in, say, our math class, and it looks like this, and I ask you, what's the average score after 3 months? So after 3 months, after we finished doing that material, if I gave you the test over again, what would be the average score? Well, since we've already got our time in months, we just simply have to plug it in. So we take the log of 4, multiply it times 9, subtract that from 80, and we get 74.58. So if this is our initial average, then we've lost some because of the material you've forgotten. Now what if I want to know how many months will pass before it drops down to a 78? Well, the average score is going to be this S of t. So I have 78 equals, here's my equation, 80 minus minus 9 log of t plus 1. So I've got to do some algebra here. Subtract my 80 over here. Divide by my negative 9. Now again, it's a common log, so that means it's a base 10. So I rewrite it in exponential form. Solve for this, and I get 1.668 equals t plus 1. So I subtract 1 for both sides, and I get t is 0.668 months. Our time is in months, remember, so that's about 20 days. So about 20 days after we cover the material, that's when the average would go down to a 78. So this is a forgetting curve. You would be given a specific one for each problem because of the fact that A and B are constants that are different depending on the class you're taking. So those are just some examples of when we can use applications of logarithmic functions. There's lots of other ones I'm sure you'll find in sciences and economics and different things like that that you do throughout your studies. Now, what about our exponentials? If you recall, we had this function a of t. Remember, this is not multiplying by t. It's saying that this is a function of t equals the principal times 1 plus the interest rate over the number of times it's compounded, all to the n's. And this was time in years. This is from section 3.2. This was when we had our periodically compounded interest. We knew it was going to be compounded semi-annually, so we put a 2 here, or quarterly, so we put a 4, or yearly, so we put a 1, but it was compounded just every once in a while. Now, if we want to have continuously compounded, so it's always being compounded, we have another formula. A of t, again, not multiplied, it's a function of t, equals the principal, and then we have that special number e to the rt. So p is our principal, and r is our interest rate in decimals. And t is our time in years. So if let's do an example of this. Let's say that we put $4,500 into a bank account. So it's invested at 7%, compounded continuously. And we want to know how much is in the account after 7.5 years. So that means that our P is $4,500. Our interest rate means our R is 0.07, and this is our T. So all we have to do, we're looking at when this is happening, what our value is at 7.5. So we plug it in. We have 4,500 times e to the 0.07 times 7.5. Plug that all in our calculator and we get our answer. A at 7.5 is $7,607.06. Remember, this is not multiplied. We do not have to divide by 7.5. All we're saying is we're looking at this particular function when t equals 7.5. All right, let's try a different scenario. What do we have So our formula is this. What happens if we want to know how long it will take an account to triple in value if it is invested at 8.5% compounded continuously? Okay, so we want to know, we don't know what the principal value is, but we want to know when it's tripled. So what we want is we want to know when we've got 3 times our principal if we have an interest rate of 8.5, so that's 0.085, and we want to know what t is. So we divide both sides by p, and we have 3 is equal to e to the 0.085 times t. Now we know that if we want to solve for this exponential, we need to put this in log form. And with a base of e, that means we're using natural log. So we have the natural log of 3 equals the exponent. Remember, base, what you're taking the log of, equals the exponent. So then we divide both sides by 0.085. And if you leave the natural log sitting there until you're doing it at the very end, you won't have to carry as many decimals, you won't be rounding in the middle. Just put this whole thing in your calculator, and then you'll get a more exact answer. So you get t is 12.925 years, which is about 12 years and 11 months. So we use this formula for compounded continuously, when you have interest compounded continuously. So that's a little different than the one we did before, but it's still similar banking equation. Make sure you've read section 4.8 and taken notes on all of that so that you can show them in class.